Can you see my screen?
Okay, yeah, maybe just try a little louder so we can hear you clear. Yeah.
Okay. Good morning. We are Team Efficient AI. My name is Xie Hui. This is a window solution for LPCV 2026 Track 1. The task is image to test retrieval on edge hardware. My idea is simple. First, make the retrieval supervision much more fine-grained and then apply acceleration. In this talk, we will focus on the data-centric part and the final accuracy efficiency trade-off.
Switch the audio. What's wrong?
This slide shows the overall problem and our research path. The platform is fixed as required. For each image, the model must rank the clear text description near the top. Our objective is to make them recall at time while keeping latency low on edge hardware. We started from the fixed clip connector as required by team and selected mobile clip to base as the backbone. Then most of all improvements come from dataset construction. Finally, we test several acceleration options, including quantization, input set acceleration, and stress set acceleration. This roadmap summarizes the full evolution of our solution. The numbers shown here are official report results. Starting from peak VIT base 32, the recall at 10 was 0.4923 with a much higher latency. Replacing the backbone with mobile clip to base immediately improved. Then the largest accuracy can come from fine-tune on our version 2 100 kilos retrieval data, raising recall at 10 to 0.6252. Text token pooling slightly reduced accuracy to 0.6248, but reduced the text latency from 4.2 to 2.7. After hyperparameter optimization, the final report result reached 0.6270 with latency reported. To understand where to improve, we first look at the bad case in sample data. The first case shows more objective separation. The ground shows asked about the mouse, but the model focused on the larger monitors. The second case is an attribute mismatch. The object category is correct, but the model confused color, shape, state, and size. The third case is a multi-object sense. One image contains monitor, keyboard, mouse, and mouse. But the model mainly describes one domain-type object. This failure told us that we need to look at object level, attribute aware negative, and multi-positive from one image. This is motivation from grounded fine-grained retrieval supervision. Visual Dreamer is a good match for these players. It's not just a caption dataset. It contains region description, object names, attributes, and relationships. This directly match the three problems from the previous slide: small object, fine attributes, and multi-object sense. So we used visual drumming as a factual source for retrieval data construction. The key point is that it did not simply add more generated caption. We tried to build a supervision that is close to how the sample queries are written. This slide explains how the version 1 and version 2 datasets are generated. On left, version 1 is a direct VM baseline. It starts from the image fault only. The VM looks at each image and generated object-centric annotation, including positives, relation, attributes, negatives, and sensitivities. Then we optionally verify the output and flash it into a contrastive JSON line file. On the right, version 2 keeps the same article scheme but adds visual geometry factor at the scaffold. We first integrate per-image facts, such as object, attribute, relationships, region, sense graph, and question-answer pairs. Then the VM uses both the image and these facts to generate bounded positive and hard negativities. This makes version 2 more factual, more controlled, and more retrieval-oriented. Now we need to define why this object-centric construction is necessary. The two pros compare text embedding from joint correction, caption, and retrieval-oriented labels. The DFNDR, which is the pre-trained dataset of mobile click tool, caption from a different distribution from version 1 and version 2. The validation test. Right here means sample data. In contrast, version 1, version 2, and validation test stay closer to each other. This means that data caption, solution, and retrieval label do not display image in the same way. For this comparison, we need training tests that live close to the validation query space. That is why all data construction focus on localized object fluid, attribute, and hard negativities. This slide compares version 1 and version 2. The core message is that version 2 is not just more text, version 2 is more grounded text. Version 1 directly asks the VM to infer labels from images, so it's fine-grained but less extractive grounded. Version 2 starts from vision more fast, so the labels are shorter, more precise, and focus on objects, attributes, and relations. The table shows the effect on the sample set. Version 1 reaches lower score compared to version 2 in the sample dataset. This supports the idea that grounded labels create better query version and clear positive negative boundaries. Here, we further validate the data direction. The left pole shows validation query coverage by training test. A higher pool means that more validation queries can stand across training tests. Version 2 is slightly better than version 1, where DFNDR is much lower. The right pole shows the nearest distance distribution. Again, version 2 is close to validation queries, and the DFNDR is much farther away. This confirms our main data conclusion. Mobile Click 2 gives strong general alignment, but the LPCV task need object-centered retrieval language. Version 2 dataset helps bridge that gap. Next, we will discuss acceleration. The first lesson is that quantization does not automatically make the model faster. On real hardware, the time may insert actual reshape and convert operation. Operation, fusion, and memory movement can also demarcate the final latency, so we did not assume that low precision must be better. Instead, we measure the real deployment behavior on the target path by QAI Hub, and only kept the motivations that improve the actual accuracy latency trade-off. What a pity, quantization is not used in our solution. Instead, input style acceleration has two parts. The first part is text token pooling. In the sample set, the effective text length is usually short. The mean length is about 24, and the next 5% is 40. So we keep internal input shape compatible, but internally reduce the text length to 40 tokens. This reduces text exact intensity with only a very small accuracy change. The second part is the image reset call, but it's make a recall. It's make is aggressive shaping hard accuracy. So we only use the text token pooling in our solution. For starter-side acceleration, we try MLP construction. That means we replace stated value activation with intervention encoder MLT blocks. We did not apply this replacement to the text encoder because the text path was limited by different hardware utilization behavior. This keeps the replacement cost to the original models. To conclude, our solution has three main lessons. First, dataset construction gives the largest accuracy gain. Dataset is everything. Fine-grained and discriminative data teach the model what to align and also what not to align. Second, acceleration must be evaluated on the target hardware. Some methods look faster in theory but can be slow in deployment. Third, the final solution is an accuracy efficiency design. It's a trade-off. We combine one version 2 retrieval data and only text token pooling and the input side choice acceleration method to reach the final readable result. Thank you for listening. This is the end of my presentation. I'm happy to answer questions here.